Hey there, welcome to the session about ICT. I'm Yuchen. I'm a software engineer from Google, and I'm a contributor to ICT OSS community. After listening to the previous sessions about Kubernetes, I'm sure you have already have a very clear or no overall knowledge and impression of Kubernetes. So finally, we'll reach to the backend data of Kubernetes. So in this session, we'll have the exploration of ICT, where the Kubernetes data rests. I'll give you an overview of architecture of ICT and some key components, which I think is very good to know. Here's today's agenda. First, I'll do the overall introduction of ICT to say what is ICT, and then I'll talk about the relationship between Kubernetes and ICT and say why does Kubernetes use ICT as a storage. And finally, let's have a deeper dive into the technical detail about how a ICT request lifecycle looks like. First thing first, what is ICT? From the official website of ICT, ICT is a distributed, reliable key-value store for the most critical data of a distributed system. The naming of ICT comes from two parts. The first part is SC. SC comes from the SC folder in Unix. D stands for the distributed, so it's very easy to understand why ICT is designed for distributed system and storing the most critical data like the configuration data. ICT is an open source project. It has a rapid growth over the past 5 years. ICT is a CNCF incubating project. It is adopted by many different projects, including Kubernetes, which is of course the most famous one. ICT focuses on some key features. Here I listed three of them, which I think is the most important. The first one is consistency. ICT ensures strict serializability by default, which is strong consistency model. It means the operation appears to have occurred in some order, consistent with the real-time ordering of those operations. For example, if operation A completes before operation B begins, then A should appear to precede B. The second feature is high availability. The recommended ICT cluster should have more than 3 cluster members, and it is designed to replicate data among cluster members. ICT leverages rapid consensus algorithm to provide strong consistency and high availability, which will improve the high fault tolerance by avoiding the failure from the single point or network partition. It is obvious if the cluster has 3 members, it will stand for the bigger failure. ICT has a high usability. It is very simple to use. You can read or write data using standard HTTP or JSON tools such as Query. As a lightweight data store, it also has a good performance. Here's a benchmark for ICT linearizable rate. Actually, if you don't mind receive the possible stale data in some condition, you can specify to use the serializable rate. It has better performance, but it just reads data from the local machine, which means it does not ensure consistency. But on the other hand, it has lower latency. ICT itself recommends to use the linearizable rate to ensure consistency. Consistency is one of the most important selling points of ICT. So how does ICT ensure the strong consistency? The first principle is that any action to take place has to be quorum, which means everything should be decided by the majority of the cluster. If the cluster has 3 members, 2 is the majority, so everything should be agreed among these 2, at least. It is the reason why ICT suggests to use odd-sized cluster. As I mentioned above, ICT builds on top of rapid consensus algorithm. There are 2 rapid algorithm properties that ensures consensus. Leader election is not one you may be familiar in Kubernetes. It is to make sure there's only 1 member in the cluster who can make decision. Other members in the cluster are followers. The leader needs to send out the heartbeats to his follower to keep his authority. The leader goes offline because of network issue. The follower will not receive his heartbeats. Then the follower will overturn the previous leadership and start a new leader election as a candidate. Basically, the cluster should always have a leader or try to elect the leader. The cluster will not serve the client request unless it has the leader. So sometimes the cluster has high leader change frequency. It will strongly reduce the performance of the cluster and also signal the potential network issue or excessive load. Log replication is another property of route. Log replication makes sure only the leader can manage the replicated log and replicate its log to the followers. The replicated log, which is named as log, should be identical on each machine in cluster logically, but most time each cluster member can have different performance and some of them can lag behind. So log records the log that are committed on the majority machine. So for example, if you have a cluster with 3 members, log records the log that are at least committed on 2 of them. On the right, here is the architecture of a replicated state machine. Firstly, the client will send the request, and the consensus model on the server will receive this request. The leader will manage the log and replicate the log entry to other followers. Then each cluster member will apply the committed log entry locally and respond to the cluster client. Even if we have the above mechanism, the cluster can still end up with corruption. The corrupted member is logically part of quorum, but the backend data is inconsistent with each other, which means the corrupted member is viewed as healthy by the peers, even if itself, but its backend data is unhealthy. Actually, it is allowed that the data on different members could have discrepancy at once, because small machine different machine can have different processing speed. However, a strong, consistent database should make sure the data at one revision number should be identical. Revision number is an important concept in etcd. I'll mention it later in our later slides. Corruption check is built on top of this property. It does a hash operation and then they compare the checksum of each member at one revision. The checksum of each member at one revision should be identical. To avoid regional cluster corruption, we need to corruption check periodically to make sure the disk data is consistent. It is very important. Here, let's move into our second part, etcd in Kubernetes. etcd plays an important role not only as a backend data store, but also for the server's discovery. Kubernetes makes use of etcd's watch operation to asynchronously monitor changes to reconfigure itself from actual to desired states. From the deployment perspective, etcd instances are deployed as pods on masters. In the regional Kubernetes cluster, like the picture shown on the right, it has 3 master nodes, and each one has 1 etcd instance. And these 3 etcd instances can form as an etcd cluster, which will communicate with each other about the leader election or other message. So why etcd is important to Kubernetes? Firstly, it's because the data storing functionality, for sure. etcd is designed to store the most critical data, and it has rather high performance, and it ensures strongest consistency. Secondly, the watch operation of etcd makes Kubernetes easier to monitor the desired and actual state. If they diverge, Kubernetes make changes to reconcile the actual states and the desired states. Then let's have a deeper dive into the etcd technical detail. Here is the etcd architecture. Everything starts from the client. The client of etcd server could be the etcd Cato, or which is command line 2 of etcd, or the API server of Kubernetes. The request goes through the client balancer and will visit one of the available nodes in the etcd cluster. Once the server receives the request, it will send out the proposal to the route. Here we can just view route as a black box, and the output of route is that the same log will replicate in WAV files on the majority machine. The consensus is ensured since all nodes follow its WAV log to apply the request. So the last step is that the nodes will apply the WAV log one by one and persist to the disk. There are two official SD ports. 2379 is for client request, listening the request from the client. 2380 is for peer communication. A peer can use this port to communicate with each other and switch the messages. If you have noticed in last slide, the backend of SAD is called MVCC store, aka multi-version concurrency control. SAD is designed to store infrequently updated data and provide reliable watch queries, which means SAD recommend to have a low rate but more read. So SAD keeps previous version of Kiwi pairs to support inexpensive snapshot and watch history events known as time travel query. That is the intuition we wanted to use MVCC data model to address these use cases. The critical concept in MVCC is revision. Revision is cluster-wide counter. It will increment each time the key space is modified, which means only put, delete, and the transaction operation will change the revision number. The range request, which is known as the read request, will not touch the key space, so it will not change the revision number. The revision works like the logical clock. It makes sure every member in the cluster can keep pace with each other. Logically, data is stored in flat binary key space, which has multiple revisions. Physically, SAD stores physical data as key pair in persistent spot DB. The key of this persistent string is a revision pair composed by the store revision as the identity of each key in the same store revision. It is not the key from the request. Value is a key pair along with its metadata. If the client requests to fetch this key pair, that is the thing which will be returned to the client finally. As a database system, SAD has a bunch of operations. Here I only list the most important ones. The first step is KV operation, the basic KV operation, which works on the SAD key space. Range is the read operation, which can read a range of KV pair lexically. Put is the write operation, and transaction is atomic if then else construct over the key value store. A transaction can atomically process multiple requests in a single request. It is widely used in Kubernetes. Since range and put are the most common and basic requests, I'll explain more about the lifecycle of them. The second type is maintenance operation, including compaction, defragmentation, and snapshot. Watch is to monitor the change of the key pair. List is to manage the temporary keys. In Kubernetes, it is used to auto-delete inventory resources. SAD also has many other operations, such like the authentication operations, which is used for authentication and authorization. If you are interested in it, you can go to the website and read the official documentation. Here is the life cycle of the put request. Firstly, V3 server will receive this request from SAD client. It wraps the request and sends the wrapped request to the wrapped cluster. Then, on each local member, they will apply the committed wrapped log entry to in-memory index string, which maintains the logical view of SAD and then writes the key pair to persistent about DB. Inside wrapped, it has these 4 steps. So, if the follower receives the wrapped request, it will forward it to this leader. Remember, only the leader can make decision. The follower cannot make the decision, so that's the reason the follower will forward the request to the leader. Leader will decide whether to create or append a new log entry, and then it will replicate this log entry to the followers. Leader will keep in touch with his followers to make sure they also commit the log entry and then update the committed index after the majority has committed the entry. After that, the log entry will be applied into in-memory index tree and also the bot DB. As for the range request, normally it should go through the same process as put request to make sure consistency. However, since it will not mutate the KV space, there is an optimization. Once Web3 server receives the request, it will get the current read index and wait until the local store applies all entries before the read index, and to make sure it is not stale. The read index is the committed index of the leader at the time the server receives the request, the range request. It stands for the latest state of the whole cluster. So once the local store is not outdated, it is safe and fast read the KV pair just from the local server. Now let's talk about the maintenance operation. I think people easily get confused on compaction and defragmentation. Both of them work on shrinking the SCD, but the integration and the object are different. Compaction works on K-space, and it is a linearizable operation which will be proposed to Raft. So why do we need compaction? Since SCD keeps the exact history of its K-space, we cannot let the K-space grow without control. This history should be periodically compacted to avoid performance degradation and the eventual storage space exhaustion. So how does compaction work? Compaction will specify a revision. Why do you set it before this compaction revision, except the latest one will be removed? Compaction is done automatically by SCD server every a couple of periods or every 10,000 log entry. But you can also request to do compaction yourself with a specific revision. Then the data will be compacted on this specific revision. Defragmentation applies on BaudDB. It is used to release the internal fragmentation back to the system. The internal fragmentation comes from the compaction operation, which is free to use by the backend, but it still consumes the storage space. Compared to compaction, defragmentation physically reclaims the space on disk. One thing we need to emphasize here is that defragmentation will block the system from reading and writing data. So if you like the whole cluster do defrag at the same time, it will stop the work. So do remember, do not like to do it at the same time, or it will break the principle of high availability. Snapshot creates the durable backup on SCD members' backend database periodically. Compaction and defragmentation will remove the history. So on the other hand, a snapshot will record the history and will be very useful to record some issue like corruption issue. Snapshot operation is done locally, so each member in the cluster can have different snapshot for a specific time. However, do remember restoring the cluster from the backup will be dangerous because you may miss the data from the time you take a snapshot to the current time. That's all I want to share about this SCD today. If you guys are interested in SCD, you can go to the website and look at the official documentation, or you can download it itself and play with it locally. Thank you.